Hi, everyone. Welcome to today's Brown Bag. It's good to see we already have about 24 people on. Hopefully we'll have a few more joining us shortly. It's my great pleasure today to introduce Dr. Hong Yo. He's from the Georgia Tech School of Mechanical Engineering and the Department of Biomedical Engineering. He's our first-time Brown Bag speaker for us, so I'm very excited to welcome him. He'll be talking about some of the work he's been doing in smart and connected soft bioelectronics. And it should be a fascinating talk, so I look forward to it. Just as a reminder, I hope we have a lot of good questions for our presenter today. Please speak up in the chat if you do have a question, and I'll try to moderate those as we get toward the end of the talk. I'll either ask your question or I can promote you and let you ask your question directly. And with that, please take it away.
All right. Thank you. Thanks for a nice introduction. And I'm going to share my slide. I hope you can see that. Right?
Yep,
okay.
Looks good.
Yeah. Again, thanks for your introduction and thanks for having me here. It's my great pleasure to introduce my research regarding smart and connected soft bioelectronics. Before jumping into my research, let me introduce my research group here at Georgia Tech. This is my group picture. Currently, we have 4 postdocs, 9 graduate students, and over 10 undergrad researchers. So as a team, we are studying a few different aspects of soft materials, flexible mechanics, nanomanufacturing, machine learning, and system packaging. So based on the fundamental study, we are trying to develop new electronics that I coded as soft material enabled electronics. And this slide captures some of my ongoing research projects. Those projects include wearable and implantable electronics and sensors. And we utilize the newly developed sensors and electronic systems for advancing human healthcare, disease diagnosis, therapeutics, and persistent human-machine interfaces. And today I'm going to focus on soft wearable electronics, and hopefully I will deliver the basics of soft electronics. And also I'm going to share with you a few examples of the applications of soft electronics as a health monitor and human-machine interface system, and also as a therapeutic system. Okay, then what are innovative aspects of soft electronics? I believe this picture captures what I'm trying to say. So as you can see that on the wrist, you see the conventional electronics. I call it as rigid electronics because it's made of rigid sensors and rigid electronic components. It's wearable system because of compliant wristband, but except that all other components are still rigid. So compared to that, you see there's another electronics mounted on the fingers, right? That's completely different from the wrist electronics because now the entire electronics is ultra thin and it's lightweight and very soft, compliant, and stretchy. So this soft electronic system has an exceptionally smaller form factor than the conventional rigid electronics. And at the same time, the soft electronics can offer better skin compatibility because of new materials that we use. Basically, it's made of skin-like materials that follow the materials and mechanical properties of the human skin. And also this device provides an enhanced signal quality when it's mounted on the human skin for measuring electrophysiological signals because of negligible motion artifacts. I'm going to go details about that later in this talk. And as I said that, or as you can see from the picture, the entire device is very small, ultra light, and ultra thin. That's why when it's mounted on the skin of a user, it has negligible thermal and mechanical burden. So by considering all of these aspects, the optoelectronics can offer long-term wearability to a user, which is completely different from the conventional electronics because the rigid electronics has limitations in that long-term wearability. So now, based on this optoelectronics, we are expecting to use this device for continuous real-time data recording as a health monitor or as a rehabilitation tool in human-machine interfaces and so on. But the biggest limitation of existing electronics are the materials. It's made of rigid and bulky materials shown on the left photo, and typically use conventional metals, semiconductors, and plastics. And we follow the rigid packaging to develop sensors and electronics. Even though we can miniaturize due to the technology advancement these days, the weight is still heavy. And also for human health and human physiological recording, it requires both sensors and electronics. That's why we still have to use multiple electronic components shown on the right. So your smartwatch is a single unit device, but it has limitations in high quality physiological signals. But we still have to use more complicated sensors and electronics that can be mounted on the skin. Compared to that, soft electronics use different materials. Now it's based on soft compliant polymers and nanomaterials. We are not using rigid and thick materials. That's why we can integrate the soft and nanomaterials as a ultra thin flexible sensors and electronics shown as photos at the bottom. So now it's very compliant, flexible and stretchy, and even it can have seamless integration to the human skin as shown on the bottom right. And you may wonder how we can design such electronics. Obviously, there are many different strategies that you can use, and many people are jumping into this domain to develop new electronics. But today I'm going to briefly share one simple idea that I'm using. So this picture shows a conventional rigid electronics that I'm holding with my fingers, right? It's miniaturized sensors and electronics packaged as a single unit. And now I can make it thin, soft, and flexible by changing materials, shown on the right. This device has exactly the same functionality as the one on the left because I used same sensors and same functional chip components so that I can maintain the state-of-the-art functionality. What I did was that I replaced the rigid plastic substrate to soft polymer. And also I removed the rigid metals of the conventional electronics to nanomembrane, shown at the bottom left. So once you reduce the thickness of rigid material, then it becomes flexible like that without mechanical fracture. That's because of significantly reduced bending stiffness, which is related to the shape and the thickness. At the same time, this device becomes flexible and stretchable based on new circuit design. So instead of using linear lines here, I developed this open mesh meant patterns so that when it's integrated with soft polymers, these metals can have outer plane buckling that can observe external stresses and strains to avoid any mechanical fracture. So based on that idea, we are building various types of soft electronics that's completely twistable, and they can include many different sensors and electronic components depending on applications. That's shown on the left, bottom left, right? So you can have conventional chip components, and then based on the idea that I just told you, based on this meander interconnects, they can observe the applied strain so that your rigid components are isolated from the external stress so that you can maintain the functionality. At the same time, the ultra-thin electrons can be directly embedded on the skin, as shown on the bottom right. Right, so it's basically moving with your skin together. It's just another layer of skin because it's ultra-thin, less than 1 micrometer. So you don't feel anything, but it has functionality to measure something and deliver the data. Okay, so those are basic information that I can share with you regarding soft electronics. I'm not going to go details about like mechanics and materials a lot. If you are curious about that, then just please email me, or you can ask me later, or you can visit my website and read my published articles. So based on this basic science of soft electronics design and manufacturing, we are using these systems as a health monitor and as a machine interfacing system and therapeutic system. So I'm going to share those examples from now. Okay, so first example is to use that soft electronics as a health monitoring system. This is the published article in the last year. So we developed this stretchable electronic system for cardiac, respiratory, and activity recording with humans. The major motivation is the following. So we are trying to measure heart activities and others as a health monitor. However, this picture shows the existing gold standard to measure heart activity, which is called as electrocardiogram. That requires multiple sensors mounted on the skin, as shown over there. And obviously, you need separate electronic components for powering and data acquisition. You have a laptop or something to get the data out of it. So it's connected by a lot of wires and so on. So basically, the system is immobilizing you so that I can get high quality data. However, these days we see rapid advancements of this heart monitor and other health monitoring systems in a way that now it becomes portable and more wearable. So most recently, the biggest biomedical company in the United States, Medtronic, they released this single device platform shown at the bottom right. So this device can measure the heart activity wirelessly, no wires as shown over there, which is very good. However, the problem is that they still use the same materials as before. It's based on rigid plastics, rigid metal sensors and others. So even though it's miniaturized, it's still heavy. That's why they have to use aggressive tape to mount the entire device on the skin, which cause skin irritation and others, and also discomfort. More importantly, once you look at the interface between the device and the skin, so basically once you flip it over, then you see that there's this rigid metal sensor contacting to the skin. As you can imagine, the rigid sensor has flat surface. However, human skin is flat. It looks like flat, but it has hundreds of micrometers in terms of wavelengths and amplitude. So when you put the rigid sensor on top of the skin, there's an air gap, which is really bad in terms of electrical signal recording because of impedance. So that's why people have to use this conductive gel shown over there. Even though it can cover the air gap, now it can cause additional problems of skin irritation, allergic reactions, and so on, based on the sodium chloride. So basically, this system is not really ideal to wear on the skin more than a few hours. So to address those issues, we developed a new flexible, stretchable system. It's still single device platform, all-in-one system that includes sensors, electronics together. And as you can see, that it's very stretchy and it's ultra thin. So total thickness is less than 5 millimeters. Total weight is less than 7 grams, including battery and everything. And it doesn't require any gels or aggressive tapes because it's super thin and ultra light. So based on natural adhesion, it can make a great contact to the skin to measure heart activities and others. Once you look at the device, it has multiple components. So at the bottom, you see there are nanomembrane electrodes making direct contact to the skin to measure electrical signals. And on top of it, we have circuit that can provide a real-time wireless data recording of those biopotentials. So basically, you can use any smartphone or tablet to measure the signals up to 20 meters based on Bluetooth. How can you really design these sensors and circuits? Typically, we follow the fundamentals of mechanics. We use finite element analysis, mechanics modeling, to design the sensors here when it makes to the direct contact to the skin. So we are expecting a lot of strain in time dynamic motion when the device is laminated on the skin. So we made it stretchable up to 100%, which is over the skin stretching limit. As you can see that it's not going to be fractured, so we can ensure the functionality of the sensors. And also there's another component circuit on top of the sensor membrane. So it's not going to have direct strain from the skin, however, still is in the soft material configuration. We're trying to ensure the mechanical safety of the circuit components. The circuit has multiple functional chips. So based on the open mesh meander interconnects design, we can isolate the strain applied to the chip components. So as you can see that it's super bendable up to 180 degrees with only 1.5 millimeters in radius of curvature. And when we measure the wireless data magnitude shown on the right, there's no change up to 20 meters when it's bent. And also this device is stretchable up to 20%, as you can see from the graph. And the wireless signal strength is still there up to 20 meters. All right, now you may wonder how we can fabricate this device, right? There are a few different technologies that we develop in our group, but I'm going to share one specific example today, which is called aerosol jet printing. So here I prepared a video clip. I hope you can see that. So that's printing of nanomaterials by using this aerosol jet printer. We make aerosol particles out of atomization process of any material that you want to use. So here we are using polymers, metals like silver and graphene, which is carbon materials as a conductor, copper, and so on. Right? So basically this aerosol system can cover various ranges of viscosity. So we can choose any ink that we want to print. And by controlling key parameters, we can print sensors and electronics like that. So for the circuit, which is the key component to measure biopotentials, we are using silver and polymer and graphene. As shown over there on the right in schematics, it has multiple layers. And then on top of it, we integrate the functional chip components. So overall, this circuit has a Bluetooth low energy microcontroller, and it has 2.45 gigahertz antenna. And it can include multiple sensors to measure heart activities and others. And also it has a motion sensor to estimate subject's motion. So by going through these processes, now our sensor was fabricated, and which is completely different from the rigid electrode that requires gels shown on the left. Because now our device is ultra thin and ultra light. Without gels and adhesive, we can have nice conformal contact with the human skin with curvilinear geometry as shown on the right. We validated through analytical modeling and computational calculations when we consider the interface between the device and human skin. We are looking at the device's bending energy, skin elastic energy, and then adhesion energy, right? And by maintaining the device's compliance and also low modulus, low stiffness like soft rubber, we can offer strong adhesion without acrylic tape that can cause skin irritation. So purely based on this elastomeric membrane, we can achieve low enough skin electrical impedance, as shown on the bottom right. Okay, without the gel, we are getting tens of kilo ohms, which is good enough to measure electrical signals. Now we are ready to measure the heart activities from the human skin. So this is how the sensor is laminated on the skin, as you can see on the right, right? The ultra thin 100 nanometer thin thick nanomembrane sensor with specific patterns follows the morphology of the human skin, right? It's not flat, it has curvilinear contoured geometry. So based on that, we are measuring electrocardiogram signals shown on the right. That's our device. Bottom right, that's the measured electrocardiogram signal, including PQRST core components that doctors monitor. We compare the signal quality with the conventional device shown on the left. And as you can see, that is pretty much similar. But more importantly, we found out that our device has big advantage compared to the conventional rigid electronics. So at the bottom, we compare our device with conventional BioRadio, BioStamp, both are wireless single device platform that can be mounted on the skin. And what happens is when a user having this device is walking or running, then you see the huge spikes in black and blue lines in the graph. Those are caused by those motion. It's very typical for existing electronics that's caused by drifting of rigid sensors on the gel. There is dissociation and motions from the sensor to the skin, which can cause these huge spikes. It's really bad because even signal processing, digital processing can kill those important aspects of data when they have rigorous signal processing. Compared to that, as you can see, the skin-like electronics has negligible motion artifacts. That's because of ultra-thin, ultra-light configuration, so that the entire device has conformal lamination on the skin, so it's basically moving the skin together, and there's no dissociation of sensor during a user's motion. So to validate that, here we took this video. I hope you can see that. So there's this guy who's walking, right? And he's wearing one of those devices on the chest, and we developed this application that can wireless measure in real time recording of the signals. The top graph is showing the electrocardiogram, which is very clear even though this guy is moving. And in the middle, that's the motion data based on acceleration. And we have the machine learning algorithm that can automatically calculate heart rate, respiration, and also we can estimate what activities is this guy doing. So this device can continuously measure the heart activity so that it can estimate any abnormality, right? Heart attack or things like that. So if something happened like this, right? Obviously it's not real, he's acting it. If that happens, then we can detect where that falling happens, we can track down based on GPS, and we can send EMS and others. Right, so that's our first example where we can use our device, the health monitor. Now, second example is about human-machine interfacing between soft electronics and users. So here we are trying to measure brain signals for wheelchair control and others. So motivation is the following. There are more than 3 million people out there in the United States who are relying on wheelchair. That's because of motor disability. And one of those main causes is coming from Parkinson's. In the United States, each year we are getting over 60,000 incidents, and it's increasing every year. And there are more than 10 million people in the world. What happens is once you have this Parkinson's and other motor disability, then you have issues of controlling your muscle, hands, legs, and others. So they all rely on wheelchair. And as you know, that typically they use a joystick to control the electric wheelchair. However, with these hand tremors and other tremor issues, they have hard time to control it. So people got this idea to measure brain signal, which is called electroencephalogram, EEG, right? So that's the conventional, typical setup that people use. As you see that try to measure, they are using this EEG cap to measure brain signals from the scalp. Obviously, it's very ugly, right? And it's very cumbersome to mount this hair cap with a lot of wires. And to enhance the signal quality, people use the gel underneath the cap, which is reacting with your hair. So every time, whenever you use this system, you have to shampoo your hair. So basically, it's not realistic. So we got an idea. We asked ourselves whether we can develop new system that's unobtrusive and real world applicable. And I got an idea based on this guy. I know some of you know that he's LeBron James, one of the best basketball players, and I guess they are doing well in this year's playoff. But the important thing is that when I saw this guy, I looked at his headband. Looks cool. So maybe I can use that idea to make our electronics. So on the right, that's the brain electronics that we developed. That includes soft electronics under the headband. So this compliance soft electronics without the gel, with soft legs, we can make a direct contact to the skin with headband. And then you can hide ground electrode, which is based on nanomembrane, on the mastoid. And there's the wireless electronic component for real-time continuous data recording. Among many different types of brain signal, we are targeting steady-state visual evoked potential, shown over there. Basically, these are signals coming from natural responses to visual stimulation. So once a user is looking at different frequencies, then by measuring the EEG signal from the visual cortex, and by going through the fast Fourier transform shown on the right in the graph, we can estimate, and we can determine the user's intention, whether the user is looking at 7 Hertz versus 14 Hertz versus 21 Hertz. So based on this idea, we built this system that has multiple LEDs shown at the bottom, right? So there are flickering LEDs, and this user who's healthy, but he's just acting that he's paralyzed, so he's not moving at all. He only moves his eyes, and he's looking at certain frequency. Then we can determine whether this guy is looking at specific frequency, 7 versus 14, things like that. And then we use that signal to control the wheelchair and others. Based on the brain mapping, that's the top view of a brain, human brain with the electrical signal strength. We validate that the visual evoked potential has the strongest signal on the back side of the head because there are visual cortex. And by measuring the data going through Bluetooth microcontroller, we can send the data to the external device. Here we are using smartphone that has embedded machine learning. Here we are using deep learning algorithm to classify and determine what kind of signal is the user looking at. And then we send the signal to the external device like wheelchair, RC car, or things like that. It is very important to have good quality of raw signals because that determines the classification accuracy. So what we did was that we compare our signal quality with conventional EEG systems shown on the left and the middle. And as you can see from the bottom graph, right, in terms of signal to noise ratio, our device shows the strongest signal. That's because of motion reduction. As I said that once you have ultra thin, ultra light device, then you can really have negligible motion artifacts compared to rigid electronics shown on the left. At the same time, it's a low power system compared to others, so we are minimizing the electromagnetic interference to have very clean data. So based on the clean data, we are going through this deep learning convolutional neural network. Here, as an example, we are using 5 different inputs to control external machine. Alpha wave, something you can measure when eyes are closed, and there are 4 frequency data based on flickering LEDs. Right, by going through the deep learning algorithm, we are getting optimal features and this fully connected layer activation to get nice output. So based on this deep learning process, we got the classification accuracy about 94% from 6 different human subjects. And currently we are getting about 100 with optimal systems right now. And now that's the example where we can use the flickering LEDs and develop the algorithm to control the wheelchair here. So there are 5 different inputs. As I said, alpha waves, there's no motion, and different frequency that we can capture user's intention that will be used as a control input for the wheelchair. So let's take a look at this video, how the system works. So there's that subject who's wearing the device on the wheelchair, and he's not going to move any limbs. He'll just look at the LED that he wants to see. There's that user intention, top left, and he's going to do certain action. And the graph will show the real-time brain signals. And then at the bottom, we will show the real-time classification output. So as you see, when he looks at 11 hertz moving and eyes closed, suddenly wheelchair was stopped. Different frequency makes the wheelchair rotate. Right? So that's an example of how we can use optoelectronics for a brain-machine interface. And lastly, I want to share how we can use optoelectronics for wearable therapeutics. Among many different disorders, we are targeting this convergence insufficiency related to strabismus, one of the eye disorders. Basically, once you have this disorder, then you see that blue box, you have doubled text, right? That's caused by blurred vision. It can cause headache, attention disorders, and fatigue for subjects. and it's impacting more than 3 million people in the United States. So basically, this strabismus has this convergence issue. From this video, this guy has involuntary motion of his eye, so he's not really converging his eye, right? So to treat this disease, doctors have vision therapy, right? To basically train people for eye versions, including convergence and divergence. So those users should go to the doctor's office, and there's this physical apparatus that includes multiple objects, moving objects with different distances. And they are practicing divergence by changing the object's distances. The problem is that, as you can see, it's office-based tools, and it's not quantitative method. So doctors purely have manual evaluation of their progress, but there's no quantitative automated metrics to tell how well they are doing. So based on that motivation, we developed this wearable therapeutic system that integrates soft electronics with virtual reality. So that virtual reality is offering the physical apparatus system, right? Instead of having that, now we are having this virtual object so that user can follow it, right? So it can be working as a home therapy system. They don't need to go to a doctor's office. And more importantly, you can change the object size, dimensions, and distances freely, right? And the system includes sensors that's mounted near the eyes so that you can track eye motions, eye versions. And you have that electronics mounted on the back of the neck for real-time data acquisition to provide quantitative feedback. We are measuring this electroacoulogram EOG signal. Basically, our human eyes are polarized like magnets. The front side is positive and back side is negative. So when you use a pair of electrode, then you can measure the polarization change when eyeball is moving to the left and right or up and down. As you can see from that graph showing like 150 microvolts change. We can validate that from this user, from the neutral eye motion, from 0 degree up to 40 degrees, as you can see that we have proportional increase of EOG potential, which is great because now, as you can see from the yellow graph, the skin light electronics can measure 13 microvolts change per degree, which is good enough to measure divergence. So based on that, we validate how the signal looks like, and as you can see, we can clearly measure the signal change when a user is looking at different objects with different distances. And based on the standard protocol, we found out that when there are 3 different objects, they have 1 degree change of the eye angle. So to determine the user's intention and what our user is really looking at to give a feedback, we developed this algorithm based on the ensemble classifier with a referral feature selection shown in the graph. So we can clearly see whether this guy is looking at near object, intermediate object, or far object by removing any blinking and other typical emotions. So through this algorithm, we got about 91% of accuracy with 6 subjects, and we are continuously increasing that accuracy right now. Here I prepared a video clip that captures how the system works. Basically, this guy is showing his intention based on fingers, not talking, and he's looking at near object, intermediate object, or far object. And our system is capturing the raw EOG signal on the top right, and on the bottom right, the classification algorithm is automatically detecting his intention. So let's take a look. right? That's how the algorithm works. So based on this algorithm, we are continuously testing the efficacy of wearable therapeutic systems with patients. And now, from this picture, you see that guy has convergence issue, which is based on strabismus. So from the red graph, that guy has an issue of convergence on the left eye. So we are working with this VR system shown at the bottom right, bottom left. Right, these are moving objects, and he's following these objects, and we are measuring his eye motions. So that's the data that we got. First attempt, we got over 70-something% accuracy, right? And when we have more trials with this guy, now we see that increase of accuracy, right? So the bottom line is that this VR embedded wearable system can really give quantitative feedback to doctors so that they can do treatment adjustment and follow-up. Right, with that, I'd like to summarize my talk. Today, I briefly share basics of materials mechanics, nanomanufacturing, and signal processing and system integration to develop smart and connected bioelectronics. And the ultimate goal of this research is to continuously advance human healthcare, human machine interfaces, and therapeutics. Thank you for your attention, and I'm thankful for research sponsors shown at the bottom. And obviously, thank you for listening. I'll be happy to answer any questions. Thank you.
Wonderful. Thank you so much. That's a great talk. I would encourage people to please post questions in the Q&A or the chat. We already have one. Noah would like me to ask this for him. Can these devices be reused? So, and even if you discard the sensor patch, can you put the electronics on a new set of sensors potentially?
Yeah, great question. Yes. We are working on two different types of devices, one for reusable, the other for one-time use. One-time use, we typically target to measure signal continuously, right? Multiple days, currently we are measuring data up to 2 weeks. So that device will be thrown away after one use, but that type of therapeutic devices, right? You only need multiple hours or less than an hour. Then it can be reused based on the material. So we change the sensor and substrate so that we make it reusable.
I see. That's great. Another question that's been posted. Is it necessary to train the deep learning model on data for a particular subject, or can the trained system generalize across subjects?
That's a very good question. That's something we are continuously working on. Initially, we train the algorithm based on new subject, but now we kind of found a way to train the algorithm with minimum number of subjects, right? Less than 5 subjects, and then we can use that generalized algorithm for other users. We are getting good accuracy over 90%, but we are continuously working on it to make it generalized use, because that's going to be important for multiple cases, I believe.
Great. Give an opportunity for the audience to post any more questions they have. So let me ask one while people think. So I would imagine that using Bluetooth is fairly expensive from a power perspective, especially for some applications you might need to transmit pretty continuously. Are you looking at power harvesting in your lab? For example, I can imagine that in some locations, skin flexion might be a way to get a little bit of power. There might be other approaches. Are you looking at that at all?
Good question. Yes, but not just muscle flexion. I guess many people are looking at that human motions, right? It gives good voltage, but very low current. So it has an issue to power, like state-of-the-art electronics and sensors. However, at the moment, we are looking at energy harvesting, RF-based energy harvesting, so that you can deliver the power wirelessly to the electronics, right?
Okay.
They can, remove that issue, I believe. And at the same time, we are also developing passive electronics, which doesn't have Bluetooth. As you said, Bluetooth has a lot of power consumption, but passive electronics doesn't include any battery, no circuit. It's purely based on inductive coupling, like electronic toothbrush that you charge in your smartphone, right? Only downside is that you have to put external coil near to devices, but depending on applications, you can wear a clothes or something on top of electronics, then you're going to wear, batteries on your skin and things like that. So there are a few different ways that we are currently exploring.
Okay, that's exciting. That's great. Other questions from audience members?
No questions.
Take just another
Obviously,
minute.
yeah. And at the same time, I think if possible, please share my email and my website so that they can visit my website and read published article or directly email me.
Okay.
If they have any additional questions.
We have a lot
I'd be happy to answer.
we have a lot of human-computer interaction students who are in this audience. Are you looking for students to potentially work with you?
Oh yeah, definitely. Depending on funding. Sadly, I already hired 3 new students this semester.
Okay.
And if I get more funding next semester, definitely. And I'll be happy to collaborate. If you have great ideas, anytime, welcome. You shoot an email, then I'll be happy to discuss.
Fantastic. Well, we do have another question that's been posted. Great talk. I was wondering if you're interested in democratizing such flexible sensors so that hobbyists, designers, or people in other fields can use this technology in a DIY sort of way.
That's an interesting question. I never thought about it. I'm not that open-minded. I'm just too focused on materials and electronics. That'll be great ideas. Why not? I'll be happy to discuss with you more. Obviously, I think price matters, right? And I guess price and manufacturing cost. That's something we are exploring at the same time, trying to make it low cost, large scale manufacturing. We're working on it based on screen printing and other inkjet printing, things like that. So yeah, hopefully, I think I'm open to that. I think that's hopefully one day I could do that.
That's great. Very exciting. We have just about a minute left, so probably time for one more question if there is one from the audience.
Lunchtime?
Yep. If not, it's probably lunchtime. So thank you again for a great talk, and thanks to all of our attendees and the people that asked questions. This was fantastic.
Thanks, everyone. My great pleasure. Appreciate it.